We're back to this Ohm's Law value with series resonance question, and what I've going to do here is show the falsity of the reasoning. Now what we've done is we've got two reactances matched to within 1%, and they are in series, and we're going to see the resultant amperage across a 2.6 ohm 1,000 feet to 14 gauge coil dual spool assembly. Now typically what everybody says is that the reactances will cancel and we will get Ohm's law. Well, let's go look then, see how true this is. We're going to repeat these observations right here. Yeah, the first observation is, let's see, that's shown in at 529 amps, 15.48 volts, giving us 2.92 ohms. That was for a different situation with different capacities. Now we're looking at the real situation. We got 5.04 amps enabled by 16.08 volts. We're going to have to write that down, damn it. Where'd my pen go? There. Okay, we got 1611. We're going to put down volts enabling 5.04 amps. Now we're going to divide that and then find the Z value. That's 3.19 ohms. Note there I had got 13.14 ohms first time I did this. Okay. Now when we got this, we just got 3.19 ohms. We got 3.14 ohms before. We see that if the current had come up to its Ohm's Law value, it should be 6.17 amps. So we're only dealing with 4/5 of the amperage occurring, according to what these people have been drumming forward in their electrical textbooks for years. Okay, this is due to distributed capacitance. Evidently, that's what everybody will say, but they should make a case in point that when they print something out, that it doesn't hardly apply to the real world at all, because of the effect of these other circumstances which are not brought into play on the explanations whatsoever. So we got 80% of the amperage, projected amperage, that we should have at Ohm's Law. What we're going to do now then is look at each reactance itself. To do that, we're going to short out the coil bank first and give us that bottom quantity. Let's see there. What's it say? Coil short, 19.54 volts, enabled 1.78 amp. The coil short is going to give us the capacitive reactance. Okay. The coil short has given us new ohmic resistance. Pardon the camera problems. The coil short has now given us 19.65 volts, enabling 1.81 amps. That's 19.55 volts enabling 1.81 amps. Okay, now we're going to do the next procedure. We're going to disattach the coil short and put it across the cap. That's going to give us the impedance of the coil system, and we're going to have to do a little further manipulation to obtain the actual inductive reactance value. So we go in there and put the short across the cap. Oops, that's a little poppy there sometimes, huh? Poppy. Okay, then we got $18.89 volts at 1.76. 18.88 volts allowing 1.76 is there? Yeah, okay. And now we'll do some calculations here real quick. We'll put it back to the resonant state. Okay, we're going to get this chalkboard up there in front of there and try to do this. The coil short gave us X sub C 19.55 divided by 1.81. That was 10.8 ohms. And now the Z for X sub L was 18.88 divided by 176. Give us 10.72 ohms. And we know that we have to subtract that by the resistance squared. We have to take that 10.72 ohms, square it, subtract the 2.6 ohms squared for the resistance. Squared minus the 2.6 ohms squared. Gives us 108 in the square root then of 108.1. Is 10.4 ohms in this example. Okay. When I measured it this time, I got a result a little different from the last time. Now it's within 4%. Or it's still yeah, it's within 4% values. Before we had less than 1% difference in values, but we still got a majority of the amperage that would be at Ohm's Law is missing. Now, why is that missing? Well, the reason it's missing is if the coil had no secondaries, if it came to its perfect value of Ohm's law, there would be no energy left to impart energy to secondaries around the primary. All the energy that could be obtained would already be on the primary. This is the reason when we do put secondaries into the picture that we get a retuning. Primaries lose a portion of their inductive reactance, and we also get reduced Q factor on the primaries. This is why reduced Q factors happen. So this is a little bit just of a lecture on reduced Q factors, and we'll hook them secondaries back up and show that magnet neon charge real quick. We'll keep an eye on our initial power input. That's tuned as perfectly to 60 Hertz resonance as we can get. We're going to add capacity to the circuit. It's got 505 amps now. Hate that. And that's the new condition of the circuit. It only went up to 5.2 amps. Okay, now we're going to connect the left coil. Left and right coils have been disabled by wire connections, so we can make the primary measurement. We'll enable them. Come on, guy, why is this not going there? I think that goes there. There's one side to the outside. There's the other side to the outside. And now our new conditions of secondary draw. We retuned the primary circuit, added more capacity, and now the conditions are, if we may note for reference, 4.2 amps at 16.3 volts. We're using a series ferrite magnet 4-inch neon bulb across the higher voltage outputs. Right now the meter would appear to be showing 424 volts over the entirety of the process and some 6.2 milliamps. And we're going to show the different voltages across that chain there and try to get that voltage meter in there. Again, we got 6 milliamps at 424 volts. Now we're going to just touch the top of the magnet with the wire that's ordinarily going to the plate, and thus we'll be reading just the amperage across the bulb. Notice that the bulb goes in and out. That's a camera idiosyncrasy, where it's taking a picture every 30 frames per second, but it might not, the bulb might not be lightened during that small time period you see where it's gone out, because time is being chopped into such small parts, and each picture on the digital conversion, whatever, shows that artifact. Okay, then we're at 4.17 volts. We'll show there's some 330 there's some 282 volts across the neon, obtained just by putting that yellow clip on the edge of the magnet. And finally, we want to see the voltage across the magnet itself. And to do that, we'd have to go right here. And there's only 60 volts across the magnet itself. Oh, what happened there? 55 volts. And that should conclude this demonstration.